Engineering Physics PPT by N. Kaushik Reddy, IIRE B section, EC B section. Here we are going to see the 3D nano carbon interconnects. Water interconnects. Here we are going to learn water interconnects. See, basically interconnects are the wires which connects the semiconductor device to chips in the device. So there are chips in the semiconductors which are present in the central part of semiconductor device. So the wires are connected to these chips which connect the connecting wires are called here interconnects. Uh, now now what are we are going to see in this PPT is introduction in scaling in integrated circuits and interconnect sources transistors and CNT carbon nanotubes as 1D interconnect structure and carbon nanotubes graphene for all carbon 3D interconnects. And summary means what we have seen in this video. uh, Semiconductor chronology. See, this is the semiconductor chronology refers to the VLSI area. What is this VLSI? It is the main part in the ECE companies. VLSI refers to very large scale integration. Very large scale integration means it refers to an IC or technology with many devices on one chip. So it can perform in cheaper. It means it in small chip only it performs like as big chip. So this technology is used in many devices or in many sectors. So the VLSI term is originated from SSI and LSI. What is this SSI? Small scale integration and large scale integration. In combination of both, this VLSI era is formed. Though the circuits involved in this scale integration are called VLSI circuits. These are used everywhere, include microprocessor in PCs. I am saying about VLSI. These are used in microprocessor and chips in graphic card and digital camera and chips in cell phone, etc. Okay. Then here we are going to see this figure 1.1. It's about brief chronology of major milestones in development of VLSI. So what are the developments in VLSI side? VLSI is its point contract transistor is before 1950s and first MOSFET it's a type of it's a type of what we call transistors, and CMOS is invented in 1963 and IC invented in 1958 and one transistor DRAM cell invented in 1968 and first microprocessor invented in 1971. So we can see here all these are invented in 20th century. Okay. Now integrated circuit trends. Integrated circuit trends where we see the graphs between the transistor per chip and minimum feature size and per year we will say. Okay, this trends in lithographic feature size, number of transistor per chip for DRAM and microprocessor MPU. Microprocessor units it stands for, and number of memory bits per chip for flash. Memory bits means MB. For flash, the transistor count for DRAM is computed as 1.5 times the number of bits on the chip of account for peripheral circuits. This is the this taken in Tower and Ning in 2009. Now, on-chip scaling driven by Moore's law. Moore's law. What is this Moore's law? Doubling number of transistors every 2 years. See, in every 2 years, the number of transistors are going into two. It means doubling. It's doubling. So that the transistors are increasing from year by year, and it's enabling more functions and reducing cost. So activities involved in these transistors are more, and it's reducing cost by day. On-chip interconnect becoming limiting factor for performance and reliability. So on-chip interconnects are becoming limiting factor for performance. Means they are reducing their capability and reliability. Now these are the graphs you can see here. Introduction. We can see the graph of transistor per chip and year of introduction when it was introduced, and the and this roads how it developed. These many number of technologies have been informed, and number and this area, and there are number of electric cars and number of electric driven bikes. Lots of technologies increasing, and there are more transistors increasing for year by year, as like traffic is increasing year by year. So to overcome this, there are many processes doing this, as we seen from right images. Then alternative interconnect materials and structures. Alternative interconnect materials and structures. What are this? Conductors with electron mean free path. And here mean free path means successive difference between 2 points, either significantly larger or smaller than those in Cu and W. Cu and W. What are these? Copper and wolfram or tungsten, and without use of barrier or seed layer. Then current carrying capacity significantly higher than Cu and wolfram. It means the current carrying capacity is more than copper capacity and wolfram capacity. So here in the diagram we see the Cu barrier seed or electroplated copper interlevel dielectric. The graph we can see it's decreasing. Resistance versus line width graph. Nanocarbons, some of the nanocarbons near ballistic transport, and current capacity is greater than 100 into copper, and high contact resistance. It has more high contact resistance. What are these silicates? Silicates means they are small grains than copper. These are smaller than copper, but whereas nanocarbons are 100 times of copper. Variation in rho with scaling. Example NiXix. So this is the wavelength, and current capacity is 10 into copper. So it we can say it is less than the nanocarbon size, and stoichiometric control of cobalt and ruthenium. No barrier. Uh, there are no stoichiometric control in cobalt and ruthenium. Now, alternative interconnects of materials and structures. Also, nanocarbons as potential replacements of copper. So, why are they replaced for copper? Because it has large capacity than copper and high intensity. So, these are replaced of for copper. Electromigration resistant. What is this electromagnetic resistance? Is its current carrying capability is greater than 10 power 8 angstrom per centimeter square. So, as this is current carrying capability is greater than 10 power 8 centimeter square, nanocarbons have the quality of electromigration resistance. So, it is replaced of copper. and it has long mean free path, high mobility and near ballistic transport. It has high mobility, means high mobility. It has more capability, or we can say the near ballistic transport, and high thermal conductivity. What is this thermal conductivity? It is the measure of its ability to conduct heat. So it conducts heat rather than um, uh, copper. It conducts more heat rather than copper. So that is why it performs the action well. And contact resistance challenges. What are this? We can see in the diagram. Those are like holes, and it's the structure of nanocarbons. It is observed under microscopes, and all 3D carbon interconnects 1D to 3D. All carbon interconnects 1D to 3D. CNT as local vertical interconnect. Graphene has horizontal interconnect and or active channel material. So these are both have sp2 bonded carbon interconnect. So both are having sp2 hybridization interconnection between carbons. You can see the structure of this uh, 3D. This is 1D structure of carbon interconnects, and here extension of superior nanocarbon properties to 3D integration. There is a extension between nanocarbon properties to 3D integration. There are lots of exchanges from 1D to 3D, and the hybridization remains the same, and sp2 bonding for high electrical and thermal conductance. The bonding remains the same, means lambda thermal conductance has higher in 3D regarding to 1D. And two possible scenarios of nanocarbon interconnects. What are may possible? We can replace completely or partly Cu and wolfram in place of cobalt and ruthenium in silicon based chips. So in silicon based chips, cobalt and ruthenium can be replaced by copper and wolfram and integrate into all carbon chips. In spite of one chip, we can integrate in all into all carbon chips. So that's the introduction about the 3D carbon nanotubes. And now carbon nanotubes has 1D interconnect structure. How are the 1D interconnect structures so formed? Objectives: comprehensive characterization of CNT wires with line width approaching those used in current technology node. Development of technique to extract contact resistance of CNT wires with line widths down to 40 nanometers. Assessment of CNT wire performance and reliability and compare with copper and wolfram. So wire performance assessment has been done with reliability and compare with Cu and wolfram. Wire text structures fabrication. Fabrication process includes a silicon hard mask for via etching to achieve vertical sidewalls. So the movement in sidewalls are changing in single phase. First, the silicon and silicon dioxide and chromium are merged. Then the walls are etched, and finally it forms in nickel stayed the corner of the walls, and CNT and then CNT has been stable, and finally a nanoprobe is formed on the side of wall which is connected with the voltmeter. So this is a test structure fabrication. Structural characterization of TEM. TEM means transmission electron microscopy. So So this is the transmission electron microscopy. What CNT near middle of wedge. Via means it interconnects with the middle of wedge. We can clearly see in the picture that the CNT is interconnected with the wedge of the chromium and a bit PT, silicon dioxide side walls. All these are seen in titliography. Electrical characterization. Nanoprobing on individual wires to measure resistance. Nanoprobing means method of extracting devices electrical parameters to use of nanoscale tungsten. So this nanoprobing on individual wires to measure the resistance of this of this semiconductor or these walls. Nanoprobing is done. So this is a picture of the nanoprobing which is done to the semiconductor chip. Okay, and right side we can observe the assumed structure of the chip, which is combined with chromium, silicon dioxide, and silicon. And this is the analysis of CNT via resistance data, which is RC's contact resistance of individual CNT log R via to log RCI by DCNT plus rho CNT into H by DCNT into ACNT bracket of minus 2 into log W carbon nanotubes. This is the formula of this RCJ. Slope of fitted log R via versus log measured data is 1.9. So this is the measure of this slope of log R via and log W. This is the graph of resistance versus height, which we seen in next before slide. R via is equal to Rm plus Rc plus rho CNT into H by ACNT. Rm is underlayer probe contract distribution. Total CNT contract resistance. Rc. CNT resistivity. Rho C total rho CNT is CNT resistivity and Rc is equal to total CNT contact resistance. And here resistance is measured in ohms and weight is measured in nanometers. It means very small. We can see the rapid growth in the graph and no cap and a bit PT cap. And y is equal to 142.52x plus 4096.5. We got the value in previous slide. And what see this is the summary of the CNT via downs to 40 nanometer with to fabricated and characterized. Best project resistance for 30 nanometer CNT via 5 into W via resistance. Current capacity is 300 mA per centimeter square. And here they gave the current capacity 300 mA by centimeter square. It means it has done very well in current capacity and more capacity we can see there. Additional contact engineering needed to reduce overall resistance. So these are the points we learned before. And CNT graphene for all 3D carbon interconnects. What is this fabrication? As I told previous, graphene growth we can see here and graphene transfer on. At last it is formed as CNT growth, and there are formed CNT is formed above the side walls of the chip. CNT carbon nanotubes You can see the changes in structure of the structure, graphene text structure of carbon nanotubes and nickel catalyst CNT grown on graphene. So, what are carbon nanotubes formed on graphene in nickel tubes? These are the pictures of that, which represent CNT grown with PECVD at 800 VDC on MLG using Ni catalyst. And summary of this CNT of graphene. CNT or graphene test structure successfully fabricated. So these are successfully fabricated, not at all unfabricated, and graphene remains intact after sputtering and CNT growth. So this it remains intact only after sputtering and CNT growth. After growing of carbon nanotubes, the graphene never after sputtering and CNT growth. CNT cross section is observed using TEM. So this cross section is observed under transmission electron microscopy. This is it is a microscopy technique in which a beam of electrons is transmitted to a specimen to form an image. So the microstructures are seen through this TEM, which ejects some beam of electrons through a specimen to form an image. So what we have seen pictures are all formed by this TEM. Further work on CNT growth and graphene with varying process parameters and contact resistant extraction. First principle calculations on CNT or GR structure in progress. Means it is in progress only. Not no one has been calculated the CNT GR structure. So this is what we have seen in this PPT. Thank you for this PPT. Thank you for this giving opportunity.